Hi everybody, today we're going to start a new topic called complex numbers, and for most of you this will be brand new material. Some of you may have seen this at school already, but probably not as much as we're going to do here. So since this is a new topic, we're going to start off with a gentle introduction. So in 3.1, that's what we're going to do today. Then we'll go through and learn some arithmetic of complex numbers, few properties of complex numbers. We'll talk more about this as we go through. Then how we sketch complex numbers in the complex plane, and then we'll use complex numbers to do a few tasks. So although this is new work for us, complex numbers have been around since about the mid-1500s. And they came out of work that people were trying to do in solving polynomials that might not have had real solutions. For example, this one, and we'll talk more about that one in a minute. And they also have many practical applications, for example, in physics and engineering. So let's have a look at what we mean by complex number. So we know from your work at school that many polynomial equations have real solutions, like this one. So if you have the polynomial equation x squared minus 1 equals 0, then we can rearrange the equation to get x squared equals 1, and we know that that equation has solutions x equals plus or minus 1, and we say that those things are real solutions, not because we have solutions that are pretend solutions, but they're real as in they're real numbers rather than any other kind of number system. But there are also polynomials, and you'll know this also from your work at school, things like this one, x squared plus 1 equals 0. And if you rearrange this polynomial, you get x squared equals minus 1. And you will have seen things at school like this, you would have said has no solutions. Or has no real solutions. And the reason that this has no real solutions, of course, is that you can't find any real number x such that x squared equals minus 1. Well, what happens then if we think about a new number? So we're going to define something that we're going to call an imaginary number, and we denote it by this symbol I. And the imaginary number I has the following property: I squared equals minus 1. So if we have that imaginary number now, then the solution to the previous equation looks like this. So we had x squared equals minus 1. And so when we rearrange this, we can take the square root of both sides, and we get x equals the square root of minus 1. And of course, we could have that as being plus or minus 1. Let me just write that a bit more clearly. And with this new thing that we've got called an imaginary number, we can then write x equals plus or minus the square root of I squared, because we said that I squared was equal to minus 1. And with this new imaginary number, that means that x is equal to plus or minus I. So one useful thing about an imaginary number is it allows us to solve equations that we couldn't previously solve when we were just thinking about real numbers. Now, just before we say something a bit more about complex numbers, be careful about the notation I. It's not a vector. So in the last topic, we had vectors that looked like that, and I told you that we were putting a little squiggle underneath the vector because, for one reason, it was going to it could easily be confused with the complex number I, and this is the complex number I that I was talking about. So we don't want to get those two things mixed up. This is a complex number, not a vector, and we denote the vector by something with a little squiggle underneath it. So we have already the definition then of an imaginary number I that has the property that I squared is equal to minus 1. So I is an imaginary number, and we're going to use that in the definition of a complex number. So our definition is that a complex number, which we generally denote by Z rather than X or Y, is some quantity consisting of a real number added to a real multiple of the imaginary number I. So if we put those two things together, it looks like this. So Z is the complex number, and it's equal to X, and X is a real number, plus Y, where Y is a real number, times I, and I is the imaginary number that we've already defined. So X is called the real part of Z, and Y is called the imaginary part of Z, and we denote it in this way. So the real part of Z is equal to X, and the imaginary part of Z, which we call Im of Z, is equal to Y. Now note that I'm not saying it's equal to YI, that's not correct. So the imaginary part of Z is the coefficient, the real coefficient of the part of the complex number that has the I. And when we take all possible complex numbers, we denote that set by the symbol C. Okay. There's lots of different ways to write complex numbers, and we're going to start off writing them in this way. Z equals X plus IY, as I denoted before, and we call this notation Cartesian form. Something else to note about real numbers, if you think about it for a minute, you'll see that the set of real numbers lives inside the set of complex numbers as a subset. And why is that true, do you think? Well, if you think about Z being a complex number that looks like this, X plus 0 times I, so I'm setting my Y in my complex number always to be 0, but X can be any real number that I like. Oops. So this is any real number. Then you can see that this is just the same as X. So this is a real number. So we can write any real number X as X plus I times 0, and that then looks like a complex number. So the real numbers live completely inside the complex numbers. Okay, so what we want to do then is write down some numbers using this imaginary number I. So for example, we can write this simple number, the square root of minus 25, and here you're going to have to remember your index laws. So remember that if I've got the square root of the product of two things, I can write the product like this, and then this is just the product, the square root of minus 1 times the square root of 25. So we know now what the square root of minus 1 is. That was the definition that we had of I, and the square root of 25 is just 5. So the answer to this is 5I. So as you can see, I've swapped the order here of the 5 and the I. It doesn't matter which way you write it. This is the standard way to write the imaginary part of a complex number. What about this one? Simplify I to the power 7. So if I have I to the power 7, this is just the same as I times I times I times I 7 times. So that's I to the 7. And we know that I we know that I squared is just equal to minus 1. So this is I squared, so that's equal to minus 1. This is I squared, so that's equal to minus 1. And I've got another I squared here, and then I've just got one I left over. So if we put all that together, we get minus 1 times I, or minus I. Okay, so here's now a complex number that has a real and a non-zero imaginary part, and we can write down the components of that complex number using these things Re of z, Im of z, and a combination of both of those things. So Re of z is just reading off the real part of the complex number. So we just take the x part of the complex number, so that's just 2. The imaginary part is the coordinate, the coefficient of I. So here's my term with the I in it. The imaginary part is the coefficient of I. So that's going to give me minus 3. And then if I take the real part of z minus the imaginary part of z, then I just get the number 5. Now, before we move on, I'd just like to point out that these things, the imaginary part of z and the real part of z, are actually functions. And they're functions because, well, what do I input into them? I input a z, so I input an element of the complex numbers. And what do I get out of the functions? I get a real number. In both cases. Okay, so for example, the example that we just looked at, the real part of z, so what I'm doing is I'm looking at the complex number, so it's a function, so I'm thinking about the real part of 2 minus 3i, so I'm putting in a complex number, and what I get out is just the number 2. So what I get out of the function is a real number. On the other hand, if I take the imaginary part, I'm still inputting a complex number, 2 minus 3i, so that's an element of C, and I get out the answer minus 3, so I get a real number out at the other end. The next thing we're going to look at is how we might sketch complex numbers in a plane. And so we've got this set up here. It looks a little bit like the XY plane that you normally used to thinking about, but you'll notice that the axes are different. So instead of having an x real number along the horizontal axis and a y real number along the vertical axis, what we have is on the horizontal axis we represent the real part of the complex number, and on the vertical axis we represent the imaginary part of the complex number. And this setup here is called an Argand diagram. Some people call it the Argand plane, and it's also known as the complex plane. And there are different ways of denoting the axes as well. So some people just have an X here and a Y here. Some people have an X here and a Y I here, or some people might put the I's on those numbers there. So you'll see lots of different ways of representing the numbers in the complex plane. So you can see that we've already got some points noted on this diagram here, and it's pretty easy to find out which complex numbers these represent. So if I go along here on the horizontal axis, that's about the point 3, and if I go up on the vertical axis, I've got the point 2. So this point here represents the complex number 3 plus 2i. So it's 3 units on the real axis and 2 units on the imaginary axis. This point here is 4 units along the real axis, and it looks like it's about minus 1 on the imaginary axis. So that's 4 minus I. Let me write that again. This point here, it's minus 2 on the real axis, and it's minus 2 on the imaginary axis, and this one here is -3 on the real axis and 1 on the imaginary axis. So it's pretty easy to read off the points off the in the complex plane. So you're thinking about the real coordinate being along the horizontal axis and the imaginary coordinate being on the vertical axis. So the next page in your notes is an example of sketching some complex numbers on an Argand diagram. So I want you to try this before you go on to the next recording. The next recording we will be talking about the arithmetic of complex numbers, but it's a good idea if you have a relook at the things that we've already done and try a couple of the examples in the book for yourself. If you have a look in the blue problem sheet book, in topic 3, the questions that you might try are 46 and 47 in topic 3. Okay, we'll go on with arithmetic in the next recording.